Hi there, the Math Dog here. In this video, I'm going to look at logical reasoning. I'm going to call this Intro to Logical Reasoning Part 1. So we're going to look at deductive versus inductive reasoning very briefly, mainly to set me up for some later videos. But I'm going to look at what we call the conditional if-then statement, the contrapositive to that statement, the converse to that statement, and what we call the inverse to that statement. So let's get started. Okay, again, topics. I'm going to look at what are definitions, postulates, and theorems in mathematics. Look briefly at deductive versus inductive reasoning. Then the meat of this video is going to be conditional statements, the converse, the contrapositive, and the inverse statement. Okay, so definitions, postulates, and theorems. A definition identifies something by describing its characteristics. For example, a circle is described as a set of points equal distance from a point called the center. A dog is a warm-blooded creature with 4 legs, a tail, etc. So the definition describes what something is. A car is a vehicle that carries passengers and is propelled by a motor. The ratio of the circumference of a circle to its diameter is called pi. Two figures are congruent if they are the same shape and size. These are definitions. They describe something. A postulate is an assumption we make without proving it, and that's how mathematics starts. You start with definitions and postulates, and from these you put them together to build other statements which you prove. So for a point not on a line, there exists exactly one line through that point parallel to that line. This is a very famous postulate from Euclid that says if you have a line and a point not on a line, there is exactly only one line parallel to that line. Parallel means they never intersect, that passes through that point. There were mathematicians for thousands of years that worked to try to prove, in fact, that this parallel postulate from the Greek mathematician Euclid was in fact a theorem, but they were unable to do that. And it wasn't until the 19th century that that was shown that, in fact, this is a postulate, not a theorem. So again, only one unique, and then through any 2 points, there exists only one line that passes through the points. If we allowed something like this, it would cause all kinds of problems in our mathematical systems. And this is called the symmetric property, and everyone's pretty common sense, but if A equals B, then B equals A. So then we have theorems. A theorem is a statement deduced by combining definitions, postulates, and other theorems together. So, for example, the sum of the interior angles of a triangle is 180 degrees. We can prove that. It didn't just come from the gods above, so to speak. All vertical angles are equal. These are example things that can be proven using postulates and definitions. Okay, then I'm going to talk very briefly about deductive versus inductive reasoning here. Deductive reasoning is what we use in mathematics. It starts with definitions and assumptions called postulates or axioms. It then combines them together to draw conclusions using what we call proof. These conclusions are called theorems. These conclusions do not change if the assumptions remain the same. For millennia, as I mentioned earlier, mathematicians tried to show that Euclid's 5th postulate about parallel lines was in fact a theorem that could be proven or proved. It was not until the 19th century, actually, I believe it was the mathematician David Hilbert, where it was shown that it could not be proven using his other postulates. So inductive reasoning is what you see in science. Starts with this should be an educated guess, a hypothesis, it's often called. It then conducts experiments to try to verify the hypothesis. As time goes on, more and more accurate hypotheses may evolve, and if validated, the result is new or modified conclusions. In mathematics, once you have your set of postulates and definitions, the conclusions can only be one, and they don't evolve or improve. You may get more theorems that are later proven in math, but unlike science, things actually are constantly evolving. I use the example here of medical science has changed over the centuries as people figured out more and more and were able to figure stuff out from their hypotheses and from just the treatment of people, which are like which is analogous to an experiment. Einstein's laws of motion more accurately describe motion than Newton's laws of motion, although Newton's laws of motion are actually perfectly fine for everything we do here on Earth pretty much. They're used for engineering and applied mathematics and applied physics. So Again, deductive reasoning is what we use in mathematics. Inductive reasoning is what we use in science. Alright, so let's talk about conditional statements. A conditional statement is also called an if-then statement. Example, all dogs are all dogs are mammals. Let's assume that to be true. Okay, we can write this as an if-then statement. Okay, if it is a dog, so I'm writing it as this as an if-then statement. If it is a dog, then it is a manual. So there's your if-then. We can also use this symbol here, which I like to use because it shortens it down, and it means that this means if-then. It also means implies. So dog implies a mammal. Okay, that's another use of the sign. Again, I like it because it shortens stuff down. So here is a Venn diagram of this situation. Dogs, in fact, are a subset of mammals, so all dogs will also be included as mammals. Notice that though not all mammals will be dogs. Which brings us to the converse. The converse switches the hypothesis and conclusion in the conditional statement. So we had the conditional statement, if it is a dog, then it is a mammal. Here's our conditional, all dogs are mammals. The converse would be all mammals are dogs. Okay? So let's write that as a conditional statement here. So I could write, if it is a mammal, then it is a dog. Okay, you can see from a Venn diagram this is false. You don't need a Venn diagram to figure this out, but there's mammals that are not dogs, like a cat, goat, and horse. So this is not a true statement. So in general, if the conditional is true, the converse is not necessarily true. And we have what are called counterexamples. Okay, these are actually very important. To prove something false, you just need one single counterexample, and for this statement here, all mammals are dogs. If it is a mammal, then it is a dog. Here is a simple counterexample that blows the whole thing apart. A cat is a mammal, which is not a dog, because the cat is out here in the mammals, but it's not inside the dog category. Only one counterexample is needed to show that a statement is false. So you only need to show one case where something's not true to make a statement false. Okay, continuing on the converse, sometimes a conditional statement and its converse are both true. This is true of definitions. Definitions can be read both ways. So for example, let's take a circle. A circle has a center. That's not a point on a circle, but it has what's called the center. All the points on the circle are like spokes of a wheel, and they are all congruent. That means they're the same shape and size. Well, in this case, they're the same length. Those are called actually radii, or radius. So a conditional statement is if a figure has all its points equal distance from its center, then the figure is a circle. But the converse is also true. If a figure is a circle, then it has all its points equal distance from its center. So definitions are we call biconditional statements, and we can write them using a double-sided arrow like this. So we could rewrite this whole thing, and I like to do this because it shortens it up a lot. We say if, and this also is pronounced if IFF, which stands for IFF stands for if and only if. So we could say IFF, if and only if, biconditional symbol. So I could read this as if figure is a circle, if and only if all its points are equal distance from its center. Okay? So if and only if means biconditional, means the statement reads true in both directions. Okay. The contrapositive. Contrapositive reverses the hypothesis and conclusion of the conditional statement and negates both of them. That means takes the opposite. So for example, again, back to our example we've been using. If it is a dog, then it is a mammal. The contrapositive would be, if it is not a mammal, then it is not a dog. Okay? And this tilde sign, often instead of writing not, we use this tilde, what's called the Greek letter tilde. That means take the opposite of also. So we could abbreviate the contrapositive as not mammal, then not dog, or not mammal implies not dog. All right, let's use a Venn diagram to demonstrate that. So we have a dog, which is a subset of the mammals, and over here then we have the not mammals. So this is a boundary between mammals and not mammals. So our thing says, our contrapositive, which is true, if the conditional statement's true, the contrapositive will turn out to always be true. So not mammal, then not dog. Well, dogs are inside mammals. Not mammals are over here. Dogs do not intersect not mammals. So some examples of not mammals would be an ant, a sturgeon, a frog, and a snake. And finally we have the inverse. The inverse negates the hypothesis and conclusion of the conditional statement. So the conditional statement might say, if it is a dog, then it is a mammal. We'll assume that true. The inverse would be, if it is not a dog, then it is not a mammal. In this instance, that would be false. So think about it. Again, this would be not dog, then not mammal. Okay. Well, if it's not a dog, we're saying it's not a mammal, but there's a mammal that is not a dog, a cat. So that's a counterexample. We have mammals that are not dogs in this case, and that discredits or proves false this statement. Okay, because again, it's saying not a dog. Well, if it's not a dog, it's saying it's not a mammal. So not mammals would be out here, but we actually have mammals that are not dogs. And a cat is the example I'm using here. Okay? So let's do an example, work through an example here with you. So let's write Michigan residents live in the US as a conditional statement. Okay, so I'm going to write that, and I'm going to use both if then and the implies symbol. And I'm going to sketch a Venn diagram. So I'm going to say here, if you live in Michigan, then you live in the US. I really like to write it the other way. So here's my hypothesis. Here's my conclusion. I like to just write Michigan implies US. Or you could write live in Michigan implies live in US. Venn diagram would be, okay, here's MI for Michigan, here's US. Michigan is a subset. Those who live in Michigan are a subset of those who live in the United States. Okay, so let's write now the converse. So for the converse, I'm going to use both the if-then statement and the if-then statement using the implies symbol. And if this is a false statement, we're going to give a counterexample. Okay, so if you live in the US, then you live in Michigan. I'll use MI for Michigan. Okay, so then live in the US. Implies lives in Michigan. Okay, well, that's a false statement, and we can give a counterexample. I'll just put CE here for counterexample. You live in San Diego, California. All right. So write the contrapositive now. Use both the if-then and the implies way of writing that. And if false, give a counterexample. So since this was our hypothesis and this is our conclusion, we would say if, let's use blue, if you do not live in the US, then you do not live in MI. Okay, well, let's look at a Venn diagram for this one. But first, let's do our symbol here. So, not live, you could actually write out not, I'm used to tilde. Not live in US implies not live in MI. So we had a Venn diagram. Here's Michigan. Here's the US. Well, if I don't live in the US, this is all not US. So clearly there's no intersection between not US and Michigan. So this is a true statement. So this was true. This was false. And finally we go to the inverse. So write the inverse. Use both the if-then and the implies form. If false, give a counterexample. So our original hypothesis was, again, if you live in Michigan, then you live in the US. So the inverse would be if you do not live in Michigan, then you do not live in the US. Okay, and that would be not live in MI implies not live in the US. Okay, well, let's take our Venn diagram again. So here we have MI, here we have US. Okay, well, if I don't live in Michigan, that doesn't mean I have to not live in the US. So here's not US, because I could live right here. Okay, and that could be Amarillo, Texas. So this is not true, this is false. Okay? Okay, here's a practice problem. We'll do these one at a time. So after I introduce it, stop the video, work the problem, and then turn the video back on, see if you agree with what I got. So write the statement, all alligators are reptiles, as a conditional statement. We'll assume this is true. So use both the if-then and the implies symbol here, sketch a Venn diagram. Okay, stop the video, work the problem. Okay, so we've got, if it is an alligator, then it is a reptile. Then we could symbolize it better or shorten it by saying alligator implies reptile. Venn diagram, and this will be true. Venn diagram, I'll put A for alligator and R for reptile. So alligators are a subset of reptiles. Okay, then we'll do number 2. Write the converse. Use both the if-then and the implies symbol. If false, give a counterexample. Okay, so I will start you out. This is our hypothesis, H. This is our conclusion, C. Okay, stop the video and do question 2. Alright, so we've got now the converse. We switched the conclusion and hypothesis. So if it is a reptile, then it is an alligator. Okay, so then using the implies, that would be reptile implies alligator. So back to our Venn diagram here. So A, R. So if it's a reptile, it's an alligator. That's not true, because I could have right here a snake, which is also a reptile, but it's not an alligator. It does not overlap the alligator subset of reptile. Okay, so that's our counterexample. Okay, the snake. Okay, so this is a false statement. The first one was true. This one's false. Okay, so now we're going to work with the contrapositive. Use both the if-then and the imply symbol. If false, give a counterexample. So just to remind you, we had our original statement A implies B. A was it's an alligator, B is it's a reptile. Remember, the contrapositive reverses the statement. It negates B and then negates A. So stop the video, write the contrapositive. If it's false, give a counterexample. Okay, so this is going to read, this was if an alligator, then a reptile. So this is going to read, if not a reptile, then not an alligator. And using the implies symbol, that would be not reptile. Implies not alligator. Okay, to help with the truthfulness of this statement, let's do a Venn diagram. So here R would be the reptiles, and inside that will be the alligators, A for alligators. Okay, so if it's not a reptile, then it's not an alligator. That's actually a true statement, because I have, these are reptiles in here, but then over here I'm going to say these are not reptiles, okay? So notice alligators completely fall inside, they're a subset of reptiles. They fall inside reptiles. They don't fall inside of not reptiles. So, example, a sheep would fit this bill because it's not a reptile and it's not an alligator. So this is a true statement. Okay, contrapositive, remember, if the original statement, the original conditional statement is true, the contrapositive will always be true. So this is not a counterexample. This is just an example to verify this statement. Okay, so finally now write the inverse. Use both the if-then and the implies statement. If false, give a counterexample. So let's remind ourselves of what the inverse is. The original statement is A implies B. The inverse is negating A and then negating B. Okay, stop the video and do the problem. Okay, so the inverse will be if not, we're negating the original hypothesis, which was if not an alligator. Then not a reptile, then it's not a reptile. Okay, so using the implies statement, this would be not alligator implies not reptile. Let's use the tilde for not here. You could write not out, but I'm using the tilde here. All right, so let's check the validity of this statement. So I got a Venn diagram. Okay, here's my A for alligator. Here's my R for reptiles. So it's saying if it's not an alligator, then it's not a reptile. But that's not true, because I could have, for example, right here, I could have turtles. They're not alligators, but they are reptiles. Okay, I could also have things like snakes. Okay, so this is false. Remember, in many times the inverse is not going to be true. If the conditional is true, only the contrapositive will also be true. The converse and the inverse are not necessarily true. All right, let's summarize what I've done here. So I'm going to let the letter A represent the original hypothesis. B will represent the original conclusion. So I have my 4 statements. I filled this out for the conditional for you. So the conditional will be if A, then B. So if the hypothesis, then the conclusion. We can also write A implies B. The converse is you're swapping the original statement, the original hypothesis, with the original conclusion. So this would be if B, then A. Okay, if we assume the conditional to be true, the converse is not necessarily true. And in the implies symbol notation, this would be B implies A. Now the contrapositive is you swap the hypothesis and conclusion and you negate them. So if not B, then not A. Using the implies notation, I could write not B implies not A. Again, this is always true. If the conditional is true, the contrapositive will always be true. Okay? Then the inverse is you just negate the original hypothesis and conclusion. So this would be if not A, then not B. Okay, then in the implies notation, this would be not A, then not B. And this is, again, not necessarily true. Not necessarily true. Let's rewrite that. That's kind of sloppy. Not necessarily true. Okay, and this concludes this video presentation. If you found this video informative and you liked it, please give it a thumbs up and consider subscribing to my YouTube channel, The Math Dog. You may share the content of this video with others. Thank you and have a good day.